everyone. Today we have Rachel from UW as our speaker. She's a professor at UW and she's going to talk about new ways to garble arithmetic circuits. Let's welcome her.
Thank you for having me here. It's actually my first time in Pittsburgh and first time at CMU. And I was welcomed with a heavy snow, which I haven't seen for a while. Very nice change. And great to see some of the students and professors here. It's like nice. All right, so this is still very intimate environment. Please feel free to interrupt me at any point. I'll try to go slow, and my goal is that everybody can kind of come along. So please don't be shy. All right, so this is joint work with Marshall Ball, Han Jun, my student, and Tianren. All right, so let me tell you. Okay. Maybe I should come to. All right. Okay. All right, so Yau's garble circuit, I'm sure that all of you have heard of it. Who has not heard of Yau's garble circuit? Okay, who has heard of it? Okay, nobody's sleeping, great. So Yau's garble circuit, it's like the Swiss Army knife of cryptography. I'm sure that nobody studying cryptography would not have heard or used it in your career. So what is it, this useful tool? So it starts with a Boolean circuit, which consists of logical gates such as OR and AND. And given the description of this circuit, it's an efficient transformation algorithm garble that takes the circuit and converts it into another Boolean circuit, which we call C hat. And in addition to the Boolean circuit, it also spits out some keys, 2 keys for each of the input wire. So Xi corresponds to AI and BI. And what does it satisfy? Given one of the key for each of the input wire, and if you want the input wire value 0, you choose AUI, and if you want input wire 1, you choose BI. And given this, what we call the labels, together with the garble circuit, you can efficiently evaluate and learn the outputs. See evaluate on X. The magic is that other than that, you don't learn anything else about the input. And this is captured by saying that given the output together with the circuit, you can simulate everything, including the garble circuit, together with the input label. Okay, so we're going to call the AIBIs as keys and the LI, which is one of them, as the label. It has a couple really, besides from the sort of the security guarantee, that it has some really nice and useful properties. The first is that the input encoding is actually really efficient. The label size or the key size is supposed to be independent of the complexity of the circuit. Okay, so typically we call it T-bits, but it's a security parameter. The second is that input encoding is extremely simple, no matter what the circuit C is. It's first of all decomposable. Each of the input bit is encoded on its own, independent of all the other input bits. So the encoding itself is just choosing one of the 2 keys. So it's extremely simple. So oftentimes, why is it useful? Because you can sort of trade off. You can prepare ahead of time this very complicated garble circuit. When it's time to evaluate an input, all what you need to send is this input encoding, which is very simple to evaluate. Okay, so lots of applications in crypto using these properties. And the most basic method, or the only method that we use to implement it, is this called the encrypted truth table method. What is it? The key observation is that all these logical gates has very tiny truth table, basically 4 rows. And what do we do to hide them? Is that we're going to pick some keys, one pair for each of the wire, and we encrypt each of the truth table row using the right combination of the keys, permute them to hide which row is which row. And now what happens is that if you're given with one pair of keys, say A1, A2, which corresponds to input value 0 and 0, you will be able to exactly decrypt one row and effectively performing the computation of AND and you don't learn anything about the 0 and the 0 part. Since the 80s, amazingly that this method is to this day the most widely applied method for garbling. But it does have its limitations. In particular, it only applies to the case where the wire values are numerable, right? So people have extended this technique to garble other kinds of gates and doing some small arithmetic computation by enumerating the truth table, but ultimately it cannot go beyond enumerating things. But you may ask that, all right, since 80s, have we not done it? That cannot be, right? There are indeed a lot of exciting works. One sort of body of work I feel is optimizing and applying this encrypted truth table method. There's an exciting line of work that reducing how many number of ciphertexts we need in order to garble one gate. For example, there's a free XOR, the half gate, all the way down. The current state of the art is each gate requires 1.5 ciphertexts instead of 4 ciphertexts as before. We can also apply using Yale's garble circuit to garble Turing machines and run computation. This is basically encrypted truth table on steroids, right? On the other hand, we do have advances in much more complex and fancy tools in crypto, and using them, we can get really fancy properties of garbling. For example, we can have reusable garbling using ABE and the fully homomorphic encryption technique. What it says is that now I can garble a circuit once, create this complicated circuit once, and I can encode the input, encode multiple inputs while reusing the same garble circuit. The flip side of reusability is succinctness, right? When something is reusable, something is succinct because you keep reusing the same thing. So another kind of very exciting line uses I/O or functional encryption are able to create very succinct garbling for Turing machine and RAM. So you can create a garbled Turing machine or RAM where the size is just proportional to the description size of the Turing machine or the RAM, not the time complexity. Right? If you think about the baseline where you convert this into a circuit, then the size of the garble circuit is going to be as large as the worst case runtime of the RAM. All right, so ultimately that up to now, if we do not use these strong tools and get these fancy properties, there's basically no significant other way of doing garbling. And in particular, all these methods only handle Boolean circuits. We're not the first one to ask this question. Applebaum, Ishai, and Kushileviz in 2014 asked the question, can we garble arithmetic circuits, which is a very natural mode of computation that appears in a lot of things, right? So here we're thinking about circuit not containing as a sequence of logical gates, where it's containing a sequence of arithmetic operation, addition, subtraction, and multiplication. It's evaluated over some ring. It makes sense to consider any ring, in fact. Your input values are ring elements, your wire values are ring elements as well. So are the outputs. Now this appears, for example, scientific computing, where the ring could be real or integer numbers. In machine learning, right? For the crypto system, then the ring could be ZP, or the ring could be the ring of polynomials. There are many, many different possible rings, and they give a different model of computation. So, can we garble arithmetic circuits? So, what do we mean by that? Here we mean that AIK defined it to be that, again, I want to efficiently convert this circuit into a garble circuit. Now, what do we do with the input labels? It used to be one out of the 2 input keys corresponding to the Boolean value of the input bit. But now the input it's not a bit, it's a ring element, right? So what they propose is that the garbling algorithm will output affine functions. Okay? And affine functions they apply on each of the input elements separately, and hence it's a univariate affine function, and therefore defined just by its coefficients, which we call AI and BI. And then they could be kind of vector coefficients. Okay, so the label affine function, instead of a scalar, I'll put it like a vector. It's really natural generalization from the Boolean case. When we think about Boolean case, just restrict this xi to a bit, you exactly recover the previous one out of the two label version. Now it generalized to an affine function over the ring. And the rest of the requirement is the same. If you're given with the garble circuit together with the input label, which is evaluate the affine function on xi, the concrete input element you want to evaluate, you will learn output and nothing else about the input.
I'm sorry. So that T is the length of the label.
T is the dimension of the
Dimension
label.
of the label.
Yeah.
So what is size T?
What is the size T? Importantly, T should be like before, should be independent of the complexity of the circuit. Right? It could be security parameter. As we'll see that later, that sometimes it could also depend on some other parameter, but it should ultimately independent of the complexity of the circuit. So that part should preserve. Another part that we observe that this way of defining more or less keeps a nice property of the input encoding. It's decomposable still, and it's very simple, right? All right. And observe that to cover this kind of circuit, we have to move away from the encrypted truth table method, which we love, and it has been extremely useful. Because the ring could be exponentially large, and there's no way for me to enumerate the values. So what did AIK show? They actually showed a theorem that we can indeed achieve arithmetic garbling. And before a very specific type of computation, they call integer computation. So basically the ring is exactly the ring of integers. But of course, when you consider the ring of integers, you're thinking about values that are not unbounded, right? Ultimately, the values are bounded by some upper bound. So they call this B-bounded integer computation, meaning that the wire values are always smaller than or equal to B. And for this kind of computation, they show that you can achieve the previous definition based on LWE. They also give a reduction, which essentially shows that you can somehow, in arithmetic setting, reduce back to Yau's garble circuit using the Chinese remainder theorem. However, that basically is sort of going back to the Boolean case. So why do we want to do arithmetic garbling? We should ask this question. There's always a baseline solution, right? Which is you just convert this arithmetic circuit into a Boolean circuit, replace every addition and multiplication with the circuit, implementing addition and multiplication over that ring, and then Yao garble it. The issue is that in this case that you kind of need the bit representation of everything. That's something that's inconvenient. And sometimes that this conversion is very inefficient. In particular, this would require us to double the implementation of the addition and multiplication over the ring. This may seem like quite trivial, but if you really think about it, even integer multiplication over the even integer addition and multiplication is quite complicated, especially multiplication. If you look at and the real world implementation, it don't just implement one particular algorithm. It does like Tom Cook, it does Carl Suga, and it does like different algorithms for different ranges of integers. And there's also a lot of hardware acceleration with respect to these. So we like to not do this conversion. Also, I am more interested in just new ways of doing garbling, right? And second of all, that sometimes that in your application, you might not have the bit representation. For example, your input is already encrypted using a linear homomorphic, arithmetic linear homomorphic encryption scheme, which you can still evaluate an affine encoding function on your input to create encryption of the labels. but you cannot do bit decomposition. More than that is that if we manage to find natural arithmetic solutions, likely it is going to get us other things, for example, efficiency, modularity, and flexibility. And this is indeed what we do. Okay, so let me tell you what we actually achieve. In terms of efficiency, we're going to use a particular measure, which I call it the rate of the garbling. It's defined as follows. It's the max ratio between the size of the garble circuit. When I talk about size, I talk about bits, number of bits to write it down, versus the size of the original circuit, the description size, times L. Well, what is L? L is the number of bits needed to represent an element in R. So if you're doing Boolean, L equals to 1. If you're doing B-bounded integer computation, L is log B. If you're doing ZP computation, then L is log P. So basically, C times L is the size of the computation tableau. How many bits you need to just write down the entire computation. And I kind of feel it's a fair measurement to charge for that when you're doing garbling. Okay, so this is how we define the rate. See a few examples. In the case of Boolean, Young's garble circuit has rate lambda, the security parameter, because that's the size of each ciphertext. So think about doing the arithmetic garbling, but doing the Boolean conversion, that I convert each of the integer multiplication into a Boolean circuit implementing integer multiplication. The asymptotic complexity is going to be L log L. So the converted circuit has size C times L log L. Then you have an additional factor of lambda, which is because you're garbling using Yale's method. This will give you some rate, which is log L times lambda, that we often measure ourselves against too.
I have a question. So
Yeah.
even for the arithmetic version, the garble circuit is still Boolean or is arithmetic?
Arithmetic version, the garble circuit is always Boolean.
I see.
So by baseline, I meant convert our arithmetic circuit into a Boolean circuit and then Yale garble it. It doesn't satisfy any of the additional nice properties when we have a direct arithmetic solution, but it's just something to compare with.
So the log L factor come from the multiplication, right?
Yes, and this is assuming we use the best kind of integer multiplication algorithm.
Yeah.
And in practice, nobody uses the algorithm because the hidden constant is too large.
Yeah, I know it's a reason paper.
All right, so our first result is we improve the AIK garbling for bounded integer computation using the assumption of Pallier, and we can achieve constant rate. So for this kind of computation, we achieve a rate that is close to constant, order 1 plus lambda over L. It means that when you are doing integer computation for very large integers, where the bits in your integers, say you have like 1000 bit integer multiplication, then this rate is constant. Comparing with the baseline, either you'll have log L times L, or the AIK solution has the rate which scales with the LWE dimension. Okay, so it's to the best we know, yeah.
Sorry, why do you need dozen bit? I thought lambda would be like 80 bits of security and L would be, if you had 80 bit inputs, so it.
Yeah, so lambda is not going to be on 80 bits. Lambda is going to be sort of the Pallier key length. Yeah, so that is lambda is actually quite big. But you would assume that if you have like 1000 bit integer computation and you have lambda, which is say 2000 bit, then this is constant.
So I thought for multiplication, like there's some asymptotically, is L log L like the best you can do? Like that's just Karatuba, L log L.
The Karatuba would be L to the 1 plus epsilon.
Okay. I see.
Trump Cook, yeah.
I see. So there's no better algorithm. Is there a lower bound for this?
I think it's not matched the lower bound. There's no lower bound, or the best is L log L. It's widely believed that's the best, but I think it's not proven.
Isn't the fast Fourier transform one?
It's like L log L log L.
Yes.
No, I think it's
one.
Yeah, the log is shaved off, but. that's
I
what
remember like Casper have some lower bound papers. I don't know if it implies the lower bound for multiplication. Okay, I'll check the papers later.
As far as I know, the lower bound doesn't match the upper bound.
Yeah.
There might be some lower bound.
And why is the dimension going up LW in L and not in the security parameter?
Oh, because no, it needs to be security parameter, but it needs to be at least bigger than L to the 1 plus epsilon. Simultaneously,
Yeah.
yeah.
So in some sense, the AI inferencing is, words kind of based on.
Yeah, you can say that. Yeah, it's especially if you think concretely, then the LW dimension is pretty good. Yeah. Yeah, okay, so as far as we know, this is the first constant rate garbling for general circuit without using IO. So previously for low depth circuits, without using IO, you can get constant rate, but not for unbounded depth circuits.
Sorry, a quick question. So for the baseline, do we need any assumption?
Our baseline is the same assumption as Yao, which is like a one-way function. All right, so our second result is that can we handle different kinds of computation? In particular, ZP computation is a very common and useful one, and we indeed can do that from either Palier or LWE. Okay? And the way it works, if you use Palier, it always gets a little bit of a nicer rate than it's sort of about lambda. If you think LWE, then it's about the LWE dimension. So the baseline would be log L times lambda. However, I do have to caution that those two lambdas mean different things. The upper lambda is the Palier key length, the lower lambda is the AES key. So concretely, the baseline has much better efficiency. But what's nice about this is that it's the first time that we can actually garble without making non-black box use of the implementation of addition and multiplication. And I think this gives much more flexibility.
And this is for all depth arithmetic circuits or?
Yeah, arbitrary depth arithmetic circuits.
What is K?
K is LWE dimension.
Oh, so how does the result compare with the first result? The first one is not for ZP.
The first one is for bounded integer.
Oh, okay.
Yeah. So our last result is that sometimes that we might consider computation, which is neither purely Boolean nor purely arithmetic. Then we call this mixed computation. And we can gamble for this kind of computation. In particular, we consider a mix of integer computation with Boolean computation. So this means your circuit, okay, so this is also naturally arise, for example, in deep neural network, that you want to do some fixed point computation, but then you have a very nonlinear activation function, for example, doing comparison, and which is much easier to do in the Boolean version. So we allow for arithmetic gates, but also you can have bit decomposition gates. And following bit decomposition gates, you can plug in any Boolean circuit that implementing some function. What we can do is that the rate for garbling the arithmetic gate is the same as the arithmetic garbling. The rate for garbling the Boolean gates is the Yang's Boolean gate. Conversion is a little bit more expensive, and depending on the trade-off, this may be worth it. Okay. All right. That's all our result, and Ryan is gonna figure it out. Any questions so far? Okay, then
There's a question on the chat.
there's a question on the chat.
Hmm.
Is an upper bound of depth of circuit required on setup? This is common with, no, it is not. Yeah, that's a separating part without agree. Unbounded depth. Okay, roadmap. What I will first tell you, now we go into the technical part, hopefully I tell you how our basic ideas are. The roadmap is that we're gonna first revisit AIK design paradigm, although they only give garbling for bounded integer computation, they do present a pretty general design paradigm that is applicable for all rings. It says that basically all you need to do is to have a garbling for addition and multiplication, which is already folklore. And the key is to design this key extension gadget. Then I will tell you at an abstract level, what is our idea of designing key extension that applies again for all ring. And then it comes to the thing is how do you instantiate the primitive we need there? And that would actually be dependent on the concrete computation you are thinking about. So I will first tell you about the bounded integer, it's simpler. And if time allows, I will tell you about the ZP computation. And I will completely skip the mixed computation part. All right. So AIK says that if you want to garble arithmetic circuit over a ring, all what you need to do is two things. One is to be able to garble for individual addition and multiplication operation over the ring. And the second is to design a key extension gadget over the ring. So let me tell you what they are. The gadgets for addition and multiplication are extremely simple. They're folklore and they're information theoretic. So let's start with the easy crack, which is addition. Suppose, remember that each of the wires have their labels. They're affine function evaluated on the wire value. Suppose that I have one wire output wire, which I want the output label to be some K0 X1 plus X2 plus K1. Oh, sorry, X1 plus X2 should have a parenthesis outside, okay, because that's the output of this addition gate. Then all I need to do is to engineer the label for the input wires to be K0, this common coefficient, multiplied with X1 and X2. And the addition part, the additive part should just be a additive sharing of the target K1, right? So if I do this, then, so this corresponds to kind of a garbling algorithm, which given the target affine function for the output wire, spits out the affine function for the input wires. Evaluation, extremely simple. Add the two labels, that's it. What about simulation? Also extremely simple. You observe that basically these two labels are random up to the condition that they should add up to the output label, right? So therefore, I can always reverse compute L2. I first randomly sample L1 and reverse compute L2. So this gives me a simulation algorithm which is using the output label as the input and spits out two input label. And what it says is that given the input label, the only thing that's revealed is the output label. All right, so what about multiplication? Also extremely simple. Let's try. Again, I have my target label value. And to do multiplication, well, I have to multiply, right? So suppose I write down these two labels like this and hide K0, X1 and X2 using random elements, R and S. If I multiply them, I will indeed get K0, X1, X2 term, which is great. I love that. The problem is that it also has cross terms, which I don't love, right? So in particular, I have X2 multiplied with R. I will also have K0, X1 multiplied with S. And I want to cancel them out. How do I cancel them out? Well, I give out more input labels, right? I did say whatever cross terms, x1, the cross term depends on x1 becomes part of the x1's input label. The cross term depends on x2 become part of the x2's input label. And how do I make sure that the additive term or adds up? Well, that's just additive secret sharing that I can always do. Right? All right, great. So that is the gadget for multiplication. Trust me that if you evaluate this way, multiply the first two labels and subtract out the cross terms, you will get exactly the output label. What about security? Also extremely simple. Observe that everything is blended. These three labels are blended with uniformly random ring elements, right? Independent also. So they are all random, subject to a single equation that needs to hold with respect to the output label. So how do I simulate? I sample the random terms randomly, compute the last input label. That's how I simulate. So the simulation tells you that given all these input labels, all what you can learn is the output label. Right? Extremely simple. Well, great. And typically that garbling are very composable. Right? So if I have more complex circuit, all what I need to do is just to garble gate by gate, right? Just in the same fashion as we have done. Now, like that's it. I have a garbling for an arithmetic circuit.
Don't it go with the depth, like multiplication, because you're giving additional information for every multiplication?
Exactly. The problem is that something has to pay. If I started with label that have dimension t, addition doesn't increase the label length. It's still dimension t. But multiplication actually doubles the input length, the label length. And what's even worse is that if you have one particular input that has large fan out, right, then its label length is going to also grow with the fan out. So these are the two sources which will cause the label to grow in length. One is due to multiplication gate, the other is due to the large fan out. So this means that in general, I will get a pretty large label dimension after a while if the circuit is deep, and hence that using this alone, you can have information theoretic garbling for log depth circuit. And this is not a very, just a common problem. Even in the Boolean case, Yale's garbling has an information theoretic version, also gets stuck at the logarithmic depth. So how can I get around this problem? Well, if the label length is a problem, let's try to extend it, right? So I need a gadget called key extension. All it does is implements an identity gate. And magically, the input label has dimension t. The label is going to be 3 dimension, much larger. And this means designing these algorithms, the GAR, the eval, and the simulation. And note that when we talk about garbling, we can also produce tables on the side for each of the gates. What we just saw for additional multiplication, the tables are actually empty. But as you can imagine, in order to do key extension, the table is not going to be empty, right? And the table is actually what constitutes the garble circuit, is the tables for all the gates. All right, so if I have this gadget, then I can solve the previous problem. When my labels become too long, all what I do is to insert some key extension gadget to shrink them back to something very short. Okay, and once they're short, then they can keep like having more additional multiplication below it. Simulation just composes beautifully, right? If I have the top output label, it can simulate the L1, L2. Then I apply the simulator on L1, L2, because they are the output labels for the next gate. That will give me next level labels. And if I apply the simulator for the key extension gadget, it will simulate both the table and the input label. Okay, so all what I need is the key extension. how can we do the key extension? Well, let's think about it. If X were Boolean, in the Boolean case, extremely simple. Now, I'll just put on the tables, which are two ciphertexts using some encryption scheme. And one encrypts C under key A. Another encrypts C plus B under key A plus B. Okay, so they look like right now, as written, they look like both scalars, but keep in mind that C and D are much longer vectors than A and B. Okay, but if an encryption scheme is supposed to use a short key to encrypt much longer messages, right? That part is totally fair. What it means that once I get the short label, which X is Boolean, so I either get key A or I get key A plus B, which will allow me to decrypt either one of the two ciphertexts, and then that gives me the right, much longer output label. Right? So this is sort of the same as enumerating the var value method. Observe that this encryption scheme is so simple. In fact, they just need to be one-time secure, right? At one time, but able to encrypt a much longer vector. Because all the label A, all the keys A and B, they change for each of the wire. And for this wire, they're just used to encrypt one ciphertext. Each of them is used to encrypt one ciphertext. And it can be a secret key encryption. Now, the question is, how do I handle ring elements? I basically need more arithmetic property from this encryption. And as you can imagine that we can use linear homomorphism. What linear homomorphism says here is that if I sort of do some operation on two ciphertexts, that uses different keys and encrypts different vectors, what I will get is an encryption encrypted under S1 plus S2 of the vector X1 plus X2. So basically, I can evaluate linear operation on both the key and the encrypted message by doing some corresponding evaluation on the ciphertext only. Then what would I do? Well, I'll just create encryption, these two encryptions. Now let's assume for now, let's cheat a little bit, that the var value is actually going to be public at the time of evaluation. We're going to fix this problem later. But suppose the var value is actually public. Then we observe that we can do this linear evaluation, which is basically multiply X and then add. What it corresponds to is a ciphertext encrypted using key AX plus B and encrypting the message CX plus D. Right? And well, this AX plus B, this key, is actually exactly the short label that we have. Then let's just like do this homomorphic evaluation to get a ciphertext. Given the short label, I will be able to decrypt it to exactly get the long output label. Extremely simple. Except that I kind of, if you really a little bit about it, then this method will work. We're pretending that the key space and the message space are both the same and they matches the ring that you're trying to deal with. Why? Because the short label is actually AX plus B over the ring. Is CX plus D over the ring. But naturally that when you're doing linear homomorphism, your linear operation on the key happens in the key space. And correspondingly, the linear operation on the message happens in the message space. They don't necessarily match the ring that you want, right? In particular, this is indeed a problem that oftentimes the key space is different from the message space. And this is going to be a challenge later that we have to solve case by case. But right now we're talking about abstract high-level ideas. So let's pretend that we don't have this problem. Now, what about simulation? Why is this a good garbling for the key extension? Well, that's because that observe, basically we're saying that the linear homomorphism satisfies this relation. And the idea for simulation is very similar as before. What does the simulator want? It wants to take the output label, it wants to show the only thing revealed is the output label. So it takes the output label and we're pretending that X is public. And it wants to produce ciphertext 1, ciphertext 2, that's the table, and also the short input label, S. Note that the ciphertext satisfy this highlighted relation, and that they're random ciphertexts. So the same idea like before, one way is that I could actually first randomly generate any two ciphertexts and reverse compute the third ciphertext, subject to the condition. So I'm gonna first compute now the output ciphertext, which is supposed to use key AX plus B and encrypt the output label. And I'm gonna compute the ciphertext 1 using A and C. So then ciphertext 2 can just be reversely computed. This actually generates an equivalent view. What's nice about it is that once in this view, observe that given S, A is completely hidden, right? Because S is AX plus B, where you have this B, which is hiding A. Therefore, my ciphertext, the security of ciphertext 1 holds. And let's say that it has a pseudo-random ciphertext. Therefore, I can just sample ciphertext 1 at random. And that's a simulation. Because as you can see, to generate this view, all what you need is L, and you can sample S yourself. And that's it. And you compute using X. So that's our high-level idea for simulation. Now I cheated a little bit before that I assumed in this process X is public, but X is a Y value technically needs to be hidden. But this is easy to fix because I can just modify the underlying computation. Before I start a key extension, I will first add the true Y value X prime with a random blinder R. And during key extension, I publish the one-time padded value as X. After the key extension, I can always subtract the R, right? And observe that the garbling is supposed to guarantee that R is hidden, and hence X, publishing X is not a problem. And if you want to see the full picture after garbling, this is how the label is going to look like. Okay, but the idea is just to blind X before you publish it. So this is the high-level idea. Basically, if we have these linear homomorphic encryption, that's very nice. We can just get key extension, and we can seemingly get arithmetic garbling for any ring, in fact, you have the right encryption scheme. So now let me illustrate to you that why.
So previously, so although the label size can be, so you label size, so one side is very long and one side is short, but the X is always in the ring. So
It's a scalar in the ring, yeah. Exactly. Okay, so now let me show you how to instantiate this linear homomorphic encryption and how to get around some of the problem. So to do that, we first focus on bounded integer computation. So to instantiate the linear homomorphic encryption scheme, let's say we use a Palier. So some basic about Palier is that it works over this group, which is Z with modulus n to the C plus 1 star. So you choose a constant C and you choose n, which is P times Q, and P and Q are safe primes. So now this group has an order, which trust me, is that number. And in particular, observe that this order is hard to compute given n, because you need to factor n in order to get P prime Q prime. And all the algebraic details do not matter. The only thing you need to know is that inside this group, it contains a quadratic residue subgroup. And that subgroup factors really well into one hard subgroup and one easy subgroup. All the elements looks like some g to the x times 1 plus n to the y. And the g to the x part is actually a hard subgroup. So G is sort of the generator in that hard subgroup. And note that this subgroup has order P prime Q prime. It is of unknown order. So we don't really know the order of this hard subgroup. The easy subgroup is generated by 1 plus n, and it has a known order of n to the c. Okay. So what do I mean by this hard group as a hard subgroup is hard? You can more or less think about it as a kind of a D-log, traditional D-log, DDH group. And in particular, it has a function called DCR, such that if I sample a random element from the hard subgroup, it's like a random element in the entire group. Okay? And in particular, one little trick I'm going to mention of the hard subgroup is unknown P prime Q prime. When you're sampling something random, a random exponent, you can always kind of approximate P prime Q prime using n, but they're not too far apart from each other. And you can just always think about the hard subgroup as a DDH group. This DCR assumption implies DDH holds in this group, and all the normal group assumptions hold. Easy group, why is it easy? Because if you actually get an easy group element, it's actually easy to discrete log. You can just compute y efficiently. So how do we usually encrypt using Clear? As you can imagine, is that I'm gonna put something random in the hard subgroup and use the fact that a random hard subgroup element is it's a random entire group element to hide the message inside the easy subgroup, right? So if I want to encrypt using key A under a vector C, I'm gonna put C in the easy subgroup. Now think about it as kind of a vector encryption, that each of the elements is encrypted in different group elements. And what about the hard element? We're going to sort of just mimic Applebaum, right? So in the public parameter, we have G to the R, where R is a vector, as long as sort of C, right? The same dimension as C. And given a key A, which is in fact just a scalar, G to the R times A is indistinguishable to pseudo-random, right? It's indistinguishable to G to the R1, G to the R2, G to the Rn. So because that's sort of DDH. So basically very similar to DDH, except that DDH would do RA Applebaum. True Applebaum is going to do exponent R times A plus the message. Here you sort of don't do the plus, you just put the message in the easy subgroup. Have I lost everyone? Okay, good. Someone telling me this, I'm already like, okay, shut up. Here, as you imagine, because everything is exponent, right? So if I just do exponentiate by x and multiply it together, what I would exactly get is an encryption under the key ax plus b of the vector cx plus d. Exactly what we want. Then I accept the problem that I always have been telling you, that I don't have the key space and the message space the same. They're actually very, very different, right? To start with, this key space is even unknown, like something I don't even know. So that we can fix because I can always pretend the key space is just integers. Okay, so I'm going to pretend that the key space is integers. Yeah.
Then why not just put the message in the hard subgroup?
Oh, then you can't decrypt unless you can discrete log.
I mean, like you can do like Applebaum, right?
Yeah, Applebaum cannot decrypt unless your message is Boolean.
Okay.
Yeah, because if you have the message in the exponent, you can't do discrete log to take it down.
So when you say it's like the integer is bounded by b, the b can be exponentially large.
B can be exponentially large, exactly. Yeah, that's the difference from the Boolean case because it's enumerable. It's not enumerable, right? My value x is already not numerable. If I have x somehow in the exponent, I cannot discrete log. That's why we like Clear, because Clear you can actually decrypt, you will get the easy group to the exponent 1 plus n to the exponent cx plus d. At that point, you can actually discrete log to get cx plus d. All right. So, but still, the key space and the message space is different. What you should be thinking about is that during the evaluation, I'm doing this information theoretic garbling, and that will give me ax plus b mod n of c. And I want to use that as a key to decrypt. But I can't because ax plus b mod n of c is not necessarily the same as ax plus b over z, right? That's always the problem that comes and bites us. So there is an easy way out if your computation is b-bounded, which is I'm actually going to use the fact that x is very small, and I'm going to make both a and b also very small, and make n to the c very huge. So the mod is the same as computing over z, right? Beautiful, beautiful, beautiful idea. Okay, that's too much like self-grandizing. And what are we going to do? We're going to pick A, which is actually fairly small because it's just a Padilla key about size Cn. That's fixed, we're not playing with it. But we're going to make B slightly larger than A times X, which is sort of B times N times 2 to the lambda. The reason we choose it to be this magnitude is, as you can see, X plus B actually is statistically close to B itself. Meaning that given ax plus b, a is hidden. Nonetheless, all values are bounded, and I just choose n to the c to be large enough so that mod n to the c is the same as over the integers. So that I have chosen n to the c kind of large, it is not that much larger. It's still, the bit length is kind of a constant in the bit length of b. And the security parameter. And security holds, I don't know if you still remember, but the key factor we used in our argument before is that given the short input label s, ax plus b, mod n to the c, it hides a. Because a is used as a key.
I remember in some previous slide you said like in simulation you just choose the ciphertext to be random so that ax plus b is random. But if that's the case, how do you bound A and B?
I just choose the ciphertext as a random. I need to be able to choose S, the conditional distribution of S, which I can. And then our generate ciphertext and our generate ciphertext 1, right? And then I just need the fact that if a ciphertext, the key is hidden, then the ciphertext looks like pseudo-random.
Well, I remember in some previous slide, there's like something like ciphertext 1 equals random or so it's now uniform one.
It's not uniform random, it's like a Padilla element, right? So it's like a random Padilla group element. All right, so that's it. That's basically the solution for bounded integer. When I get to the short label to do key extension, I interpret it as a value over z, and I decrypt. I homomorphically evaluate the ciphertext, and I decrypt the ciphertext to get the longer label.
Question?
Yeah.
So is the number of multiplication limited?
Not
Otherwise, it will like, if we multiply many times, will it exceed like n to the c?
This is a bounded integer. It means that the model is that all the wire values are bounded by b.
So if you multiply by 1, it's fine. You can multiply polynomially many times. Just make sure you multiply by 1. Then it will be bounded.
So the number multiplication is
A weird model of computation. You cannot handle arbitrary integer computation because, as you said, the value may go like the individual value may become exponential bits, right? You can't handle that anyway. So imagine that you have an integer computation But the wire value ultimately have to be bounded for your computer to run it.
Oh, I guess my
Yeah.
question is, I understand like A and X are small, but if we like apply multiplication many times.
So you know the bound first, and then you choose your parameters. It's not that I choose a parameter and I can handle arbitrary bound.
Okay,
And
Does
you
that make
know the bound once you know the circuit, right?
Yeah.
Okay, so
You
you get
know
the
the
circuit,
bound.
then the bound, then the
Yeah.
parameters. Okay.
Yeah, you know the circuit and you know a bound, and then you choose the parameter to garble it.
okay, so I know the circuit first,
Yeah.
then has the like a topology.
So
Yeah.
in general, like what's the dependence on it? So there's like some implicit dependence on the depth in the set, right?
Yeah.
If you're not multiplying by one.
Yeah, it depends on your model of computation.
Multiplication is just a polynomial blow up, and B is already exponential, so I think it's fine.
But if the circuit, let's say, just had multiplication gates, like a
Then,
balance,
yeah.
there will be fancy one, right?
Yeah, I think otherwise it will blow out. Yeah,
There's a question in the chat.
okay. Do you need to be able to obliviously sample valid ciphertext for simulation, hence using DCR? I do need to be able to obliviously sample, yeah, ciphertext. Okay, so quickly just to walk through, as you can imagine, like using LWE, we can also very easily implement linear homomorphic encryption. And then what is going to happen there is that your homomorphism is not going to be exact. There's always some noise floating around, which is annoying, you need to handle. And this problem comes back and bite us in the sense that the key space in LWE is actually going to be ZQ, which is the LWE modulus. However, your message space is slightly smaller. It's ZP, where P is smaller than Q. Why? Because you always need to separate your message from the noise. So you cannot hope that your message space is also ZQ. If that's the case, then you cannot separate the message from the noise. So this again is the problem. What we do in the bounded computation case, very easy. Make sure that everything is smaller than P. So when I get the label AX plus B mod P, it's the same as over Z. Now everything falls apart when we go to the ZP computation, which is much more complicated, and that's why much harder. What's the key problem? Is that let's think about the LWE version, that I have message space ZP, and I have key space, which is over Z. What happens is that I don't have that bounded trip, because it used to be my value is smaller than some fixed bound, but now I don't. The value is some ZP element. That's the computation itself, right? So certainly in this case, AX plus B mod P is very different from AX plus B over Z. Make sense? That's the difficulty. So what are we going to do? This is sort of like a little bit like pulling a rabbit out of a hat. I'm gonna first think about some very simple distributions of A and B, and I will just think about the scalar version, not the vector version, so that I can actually recover AX plus B from AX plus B mod P. And I don't have any restriction on X. X could be as large as possible. What we're gonna do is that we're gonna first make A Boolean. Okay, A used to be our key. This is Boolean, so this will be a problem later, but nevertheless. Next, I'm gonna choose B from this special distribution, which is not even completely random out of P. Either it is a random value between 0 and P over 2, or it is a random value between P over 2 and P. And the case depends on the value of A. So if A is 1, it's smaller than P over 2. If it's 0, A is 0, it's bigger than P over 2. Weird, right? Who thinks about this distribution? You have to look at the plot. Okay? So remember that I want to recover AX plus B over Z. So let's plot the value, how it looks like. This is from 0 to P. And let's first look at the case where x itself is small, smaller than p over 2. Now suppose a is 0, well, then that basically means I'm gonna get b, right? So that's between a random value between p over 2 and p. Now suppose a is 1, I'm supposed to get x plus r, which is a value that sort of like is here, or it could be here, because p is smaller than p over 2. But in other cases, there's no wraparound, right? This is always smaller than p. Then if there's no wraparound, I always know that s prime equals to s. S is the mod p value. Fantastic. What about if x is bigger than p over 2? Again, in the a equals to 0 case, the range stays the same. In the case where a is 1, then because x value is big, and then you sort of get here, you do wrap around, right? Now, observe that if, what do I observe at the evaluation time? I know what is x, and I know what is s. Suppose s is here, smaller than p. There's no wraparound. S prime equals to s. Suppose s is actually smaller than p over 2. It means it's actually the highlighted region. It had wraparound to come over to the small side. Then in that case, I just need to add p to it. Right? So in this very weird distribution, I can actually recover the integer value. Now the question is, do I have any security with this weird choice of distribution? Because I don't want a to be hidden. A is a key, and that's important for security. We observe that this is the same plot. I just now plotted the mod p value where we have this wraparound here. When would a be hidden? It is when the value of s falls into the overlap. Right? You know the value of x, that's public. So whenever you get a value that's in the potential overlap region, you don't know if it's the top case or the bottom case. Meaning you don't know if a equals to 0 or a equals to 1. Does that make sense? If you are here, then obviously you can read off. If you are outside the overlap, you immediately read off the value of a. But if you're in the overlap, then you have some limited probability that a is hidden. And the probability equals to exactly how large the overlap region is divided by p over 2. So by looking at this probability, you realize that if x is actually far away from the two ends, it's sort of in a middle region, then the overlap is pretty decent. And you will have that with probability half, a is hidden. At least something. So there are 2 problems. One is that, okay, a is hidden with probability half, but it's not good enough for a key. What do I do? The other is, what would happen if x happened to be at the endpoints and a could be completely revealed? To solve the first thing, it's very easy. I basically aggregate lots of a's, but I need to do it in a little bit careful fashion because I need to aggregate over z because the key space is z. So I cannot directly use leftover hash lemma. That would require a finite field. But nevertheless, we prove a lemma, which we call the seeded smudger, shows that you can actually aggregate over z. What happens in the bad case? If my x is at the ends, and now it can be just completely revealed. Well, in particular, when a is revealed, it means that you have both a and b. You will run both a and b, and hence you will run both c and d. There is no security left. But the nice part is that x or x plus p over 2, one of them has to be good, right? So I should just simply share. I'm going to duplicate my key extension, one with completely random a and b's. One copy uses value x, another copy uses value x plus p over 2. one of the copy is going to be secure, meaning in that secure copy, A and B, C and D, their individual values are hidden. And all what you learn are the linear combinations. What do? It means that the actual key, the label I should use, is the sum of both of them. And that corresponds to some specific actual C and D. All right, so that's that. In summary, we achieved these results, and I'm sorry, I'm running so late. I have a few open questions. One is constant rate garbling. Can we do it for more different models of computation? Can you do it for ZP computation? Can you do it for Boolean computation? And this would be very different from what we know right now. And there is a question about arithmetic garbling. It seems like very interesting that for every ring we have to work very hard. And indeed, there's some reason for it. We know there's no garbling that is black box in the ring. If you have such a construction, then you automatically have the garbling for every possible ring. But there is a question which is, can you have the garbling that just the garbling algorithm is black box in the ring, but the evaluation could be non-black box in the ring. That's open. And can you do it from other assumptions than Pavir and LWE? And that's it. Thank you. Sorry.
For the secret sharing part, so like so only one of them is like more secure. So how do you like combine it? So you like just keep both of them, like.
Yeah, so we're combining by just adding them. So the actual key extension is gonna run these two parallel versions and then add the output label and use that as the actual output label. You use L bar as the actual output label.
Okay, so the actual output is still in ZP.
It is in ZP, yeah. Everything is one P, you see.
Can we use like we don't need full-fledged LHE, right? We just need LHE for constant number of ciphertexts. Is that right?
Yeah, you just need for like, you need to be able to do this univariate affine function.
And the problem is really the noise which grows, like with LWE. It interferes with the ZP computation.
Yeah, that's why you have to make the LW modulus much bigger than ZP.
Have you tried using LPN where the noise is like very sparse over ZP?
Oh, yeah, then the problem is that I don't know how to hide the, there is a problem. I don't know how to hide the, yeah, so there is a decryption, right? Because you actually decrypt. You actually do decrypt. At the time of decryption, you're gonna learn some noise. In the LWE case, I can claim that this noise doesn't leak information. But however, in the LPN case, I cannot, yeah.
There's a question in the chat.
Does this construction to double is good? No, we don't consider adaptivity at all. I don't know. I haven't thought about the adaptivity question. I have no idea, yeah.
Our question, so the TD is something where you garble circuit, you create a table that is like public.
Yeah, so you're at garbling, you're gonna sort of create all those tables, and then the garble circuit is all the tables.
So TD counts to the size of the garble circuit.
Exactly.
Is the round complexity the same as Yale's complexity?
What do you mean by round complexity?
So in the Yale's, you need to have one amount of OT and then send the circuit to another guy. In here, is it the same?
Yeah, I think it's pretty similar. You just swap OT with OLE, which is a previous linear evaluation that can do this sort of like affine function.
Okay, you said that there's some public. Oh, the public problem is solved by the random cover like, plus R first and then minus first.
Yeah, yeah, that is solved by that, yeah.
I guess if there's no other question, let's thank Rachel again.
Thank you. So late and you guys are still up and around.